Hello, ladies and gentlemen. Let's get right to circular motion question 1. A man runs around a circular track of radius 100 meters at constant speed and takes 168 seconds to complete a revolution. Considering the movement from A to B, calculate the angular displacement. So the angular displacement in this case will be 90 degrees or pi over 2 radians. Now we can't write pi over 2 radians because we can't leave it in a fraction, so it's not accepted. So we change it into 3 sig fig instead. Okay, and then we must put anti-clockwise because that is the direction of his travel. Now next, what is the distance traveled? The distance traveled is easy to compute. Is S is equals to R theta, which would be 100 multiplied by 1.57, which is 157 meters. Next, what is the displacement? Now the displacement is a little bit more tricky because the displacement is the straight line displacement between A and B. So this is the displacement S, and it's 100 over here and 100 over here. So S will be the square root of 100 squared plus 100 squared. That would be actually 141 meters. Now what is the time taken? The time taken will be 168 seconds divided by 4, which will give you 42 seconds. So what is the speed? Now the speed will be the distance divided by time, and this distance over here will be 157 divided by 42, and that will give you 3.74 meters per second. What about the average velocity? The average velocity will be the displacement divided by time, and the displacement divided by time would be 141 divided by 42, which will give us 3.37 meters per second southwest. What is the instantaneous velocity A? Let's draw it in the diagram. The instantaneous velocity at A we call VA. What is the instantaneous velocity at B? At B we call it VB. Alright, so the instantaneous velocity VA can be given as the following. VA is equals to R omega. So R omega will be 100 multiplied by 2 pi divided by 168. Okay, so that will be the instantaneous velocity at A. What is the change of velocity? And draw it in a diagram. So let's take a look at VA. VA is in this direction and VB is in this direction. So the change of velocity will be the change from VA to VB. This will be delta V. Now let's first calculate what's the VA, and then after that we'll calculate what is VB. So we know from the previous question and also from our calculations that VA is 3.74 and VB is also 3.74. So added together, delta V will be 5.29 meters per second southeast. Okay, and this should we have to draw it in the diagram. Okay, so in order to draw VA and VB, delta V will be drawn starting from here in the middle of arc A and B, and this would be delta V in this direction. Okay, or you can draw it like this, delta V in this direction. Now because delta V is a change of velocity, I tend to draw it with 2 arrowheads instead of 1. So this is question 1. Now let's take a look at question 2. A turntable rotates at 33.3 revolutions per minute. Okay, a turntable is basically an object with a motorized disc in the center. So very often it's used to play records. Okay, so this is a turntable. Right, so express the angular velocity in radians per second. Now the angular velocity can be expressed as 2 pi f, which will then be given as 2 pi 33.3 revolutions per minute. All right, so that will be 33.3, and then we need to express it in seconds. So that's 33.3 divided by 60 seconds. Right, so this would be 3.49 radians per second. Calculate the frequency and period of the rotation. Very easy. The frequency will be 33.3 divided by 60. and the period of the rotation, all right, will be the time required for one rotation, which will be 60 divided by 33.3. Right, so that will be it. Now calculate the linear speed of a wooden block placed 10 cm from the center. The linear speed of a wooden block is given by V equals R omega. So that will be 0.1 because it's 10 cm from the center multiplied by 3.49 radians per second. So the answer will be 0.349 meters per second. Now the block is placed at a distance away from the center of the turntable. Sketch two separate graphs to show how the velocity and acceleration varies with distance from the center. So the first thing I'm going to do is draw V against R. Now, if we write the equation for V is R omega, where omega is a constant, then V against R will be a straight line with the gradient being omega. Now let's draw the acceleration against distance from the center away from the turntable, and if we write the equation, it's A equals R omega squared, and we know that omega is also a constant, so this will be omega squared will be the gradient. Now let's take a look at question 3. A man stands on the equator of the Earth. The radius of the Earth is as such. Calculate the man's angular velocity in radians per second. Now, the angular velocity of the Earth is given by 2 pi divided by the period of the Earth. Now, how long does the Earth take to rotate around one period? Answer is 24 hours. So 24 hours converted into seconds will be 2 pi divided by 24 times 3600. That will be 7.27 times 10 to the power of minus 5 radians per second. So if you are standing on the equator, what is your linear speed? Your linear speed will be given by the radius multiplied by angular velocity. So that will be 6.38 multiplied by 10 to the power of 6 multiplied by 7.27 times 10 to the power of minus 5. And that will give you 465 meters per second. So can you look out at yourself and out the window? Everything you see around here is moving at 465 meters per second relative to the center of the Earth. Now, what about someone resting in London? Will he move at the same linear speed or will he move slower? Now, let's take a look from the North Pole. So if I view it from this point of view, top view, if I view it from the top view, then you can see that the North Pole is over here, and this is where London is. This is where London is. And this is where Singapore is. Of course, Singapore is not at the same place as London. Singapore is somewhere over here. So Singapore is moving with a very high linear velocity. London is moving with a bit of a less linear velocity. The reason is because the radius of rotation around the Earth's axis for London is a lot smaller than the radius of the Earth's rotation at the equator. So this is R equator, this is R London. Alright, so now we need to find out what is the radius of rotation around London. The radius of rotation at London will be equals to the radius of the Earth multiplied by cosine 51.5 degrees. How so? Let's take a look at this plot of the Earth. Okay, this is R, this is R, this is 51.5 degrees, this is RL, and this is RE. Okay, alright, so RL will be equals to R Earth cos 51.5 degrees. So then the linear speed of the Franz motion, the linear speed of the Franz motion will be omega at London. Velocity at London will be equals to R at London multiplied by the omega of the Earth. Okay, so that will be 6.38 times 10 to the power of 6. That's the radius of the Earth multiplied by cosine 51.5 degrees multiplied by the omega. And the omega value will be 7.27 multiplied by 10 to the power of minus 5. And so that would be 290 meters per second. So notice that the London guy is moving much slower than the Singaporean guy. Okay. And this is question 3. Now, let's take a look at question 4. In question 4, the key concept of the question is that the work done by the centripetal force is 0. Now, why is the work done by the centripetal force 0? There are two reasons. Number one, you can say that the net work done by a force is the same as the change in the KE of the force of the body. Now, let's take a look. The body moves at a constant speed v, which means that the KE is not changing. So it's no change in KE, so hence no work done. So the work done is 0. Now, the other way of thinking about it is that, now, if a body is moving in this direction, all right, the force that is used to accelerate the body towards the center of the circle, the force providing a centripetal force, is always perpendicular to the direction of motion. So this is the velocity of the body, and this is the force, F. Now, you know that work is equals to F d cos theta, and in this case, theta is equals to 90 degrees. So cosine theta is equals to 0. So no work done if the force is perpendicular to velocity. Now, how about momentum? Okay, so from the object moving from x to y, let's take a look at the momentum over here. This is point x, and this is point y. So the object is moving in this direction. The momentum is mv. Now over here, the object is now moving in this direction. The momentum is now mv. So this is p2, this is p1. Now p2 minus p1 is equals to 2mv. If you don't know why, alright, just take note that the two momentums are in opposite directions. So in order for the p2 to minus p1, this is the change in momentum. This equals to 2mv, twice as much as either p2 or p1. Alright, so over here, the work done will be 0 and the change in linear momentum will be 2mv. So the answer will be C. Right, so this is question 4. Alright, let's take a look at question 5. Now, the key concept in question 5 is to ask yourself the question, what provides centripetal force? So let's take a look at this object over here. Now, this object is stationary. So, if we look at this 1 kilogram mass over here, there are two forces acting on the 1 kilogram mass. The first force will be mg and the second force will be T. And then in this case, since the object is stationary, T equals mg. So what is m and what is g? So this is 1 and this is 9.81. So T is equals to 9.81. Now the tension in this string over here is 9.81 newtons. So since in A levels, the tension in the string is constant throughout the string for A levels only. Okay, so this is also 9.81 newtons. So the tension in the string will be 9.8 newtons. Now let's calculate the tension speed of the puck. Now, so we'll ask the question, what provides centripetal force? So we say tension provides centripetal force. Okay, so we'll then fill in 9.81 is equals to the mass of the puck is 0.25 kg. So it's 0.25 v squared. The radius of the puck is 1 meter over here. So that gives you a speed of 6.26 meters per second. Now, if the speed of the puck is decreased, whether or not your mass should be increased or decreased to maintain uniform circular motion of the puck. Let's take a look. If the speed of the puck is decreased, the centripetal force required will decrease. Since the tension provides centripetal force, so the tension must decrease. And so the weight of the mass below must also decrease. So here's the logic. Now, since the tension provides centripetal force, okay, so what happens is if V decreases with M and R remaining constant, then the tension must also decrease. So this is for the puck. What about the hanging mass? For the hanging mass, T is equals to mg. And I think you can see where I'm going, right, over here. So if the T decreases, then the mass of the hanging mass must also decrease. All right, so this is question 5. Now let's take a look at question 6. Now in question 6, once again, the key concept is what provides centripetal force. So over here we have an aeroplane with a lift of P and then a weight and a radius moving around in a circle as follows. So the first thing we've got to do is to resolve the P into horizontal and vertical forces, right? So looking at this trigonometry, this will be P cosine 35 and this will be P sine 35. Now, if we answer the question, what provides centripetal force, then P sine 35 is the one that provides centripetal force, mv squared over r. And what about P cosine 35? So P cosine 35 balances the weight. So now we have these two questions, we can start doing the question. We've got these two equations, we can start doing the question. So let's first calculate P. Now P cos 35 equals to mg, so then we can write P cosine 35 is equals to the mass of the aircraft is 4 times 10 to the power of 4, and the g is 9.81. So this gives us a P which is equals to 4.8 times 10 to the power of 5 newtons. So this is the lifting force of the aircraft, lift force. So calculate the centripetal acceleration of the aircraft. This one is a little bit more challenging, but let's take a look at centripetal acceleration. Now you notice that the centripetal acceleration is v squared over r over here. So if we use this equation down here, we say v squared over r is equals to acceleration, centripetal acceleration, which will be P sine 35 divided by the mass. Okay, so if you fill in the values over here, that will be 4.8 times 10 to the power of 5 sine 35 divided by the mass of the aircraft, 4 times 10 to the power of 4, and that should give us 6.9 meters per second squared. Now, so calculate the radius of the path of the aircraft's flight. So v squared over r is the centripetal acceleration, and then we know that the velocity of the aircraft is 250 meters per second. So what this means is that 250 meters per second over here, we square it, divided by r, will be 6.9. So r is equals to 9100 meters or 9.1 kilometers. And calculate for the time taken for the aircraft to complete one full circle. Now this is quite easy. The time taken to complete one full circle is the circumference of the circle divided by the velocity. So it is 2 pi times 9100 divided by 250. So this one gives us 230 seconds. Now express the turning radius r in terms of m, theta, g, and v, and hence describe how the mass of the aircraft affects the turning radius. Okay, so now we are going to have to combine these two equations over here. All right, so if we use P sine theta is equals to mv squared over r, and then P cos theta is equals to mg, then we do an abracadabra, we will get tangent theta is equals to v squared over rg. And you find that is no m in the equation. So what this means is that the turning radius is independent of the mass. Okay. So over here, P sine theta provides the centripetal force. P cos theta equals mg. So tangent theta is equal to v squared over rg. So that for any particular banking angle and speed, the turning radius is independent of the mass of the aircraft. So sometimes I like to ask my students this question. So here is a passenger liner. Okay, passenger aircraft is very big and very massive. Okay, and it's turning at an angle of about 35 degrees. And then here is a jet plane. Okay, here's a fighter jet, which is really a very fast moving aircraft. Okay, a very fast moving aircraft, a fighter jet, also at an angle of 35 degrees. So the question is, which one has a smaller turning circle? Which one has a smaller turning radius if they are at the same speed? And the question is, neither. They both have the same turning radius. Okay, so this gives you a little bit of food for thought about Top Gun and everything else. Of course, that is only true if the lifting force P is like doesn't have any other special stuff. But of course, modern jet planes have thrust vectoring and other weird stuff. Okay, involved. You know, the 5G fighters can have a very, very small turn radius because they are not performing circular motion. The motion that they perform is turning on the spot. Okay, so this is it for question 6.